Welcome to the Rich Report, a podcast with news and information on the world of high performance computing. Today, my guest is from Warp Mechanics. Once again, we have Josh Judd. Josh, welcome back to the show.
Thanks for having me.
Well, thanks for coming on, Josh. We ran into each other last week at the Stanford HPC conference, and I thought it was time to catch up and learn more about what's going on with Lustre and ZFS and all the things happening at Warp Mechanics.
I'll just jump right into it then. I've been giving presentations at supercomputing and lug and other shows for quite a while on ZFS on Linux, and we have some exciting updates as of this year on the conversion of these to file system technologies. So that's going to be the subject of the talk. Go ahead for the next slide. In overview, we're going to talk about, well, first of all, what is Lustre over ZFS and why is it relevant to you? What is the customer benefit of this architecture? Then I'll just briefly remind listeners where we were at last year with integration. What was the state of the art? What have we done since then is the primary topic of the conversation, and I'll give some concrete examples of how Warp Mechanics implements ZFS Lustre integration. However, all of this is open source technology, so you don't necessarily have to buy anything from us in order to get this solution, which is one of the great things about it. Now, why do you care? Why would you go to the trouble of building a Lustre over ZFS environment? And how would you actually go about doing it? That's the agenda, if you will. So, jumping right into it, next slide. What is Lustre over ZFS? Well, Lustre is a horizontally scalable file system, as pretty much all of your listeners are already aware. It sits on top of normal file systems. So I call a meta file system a file system of file systems. Lustre is a file system built on top of other file systems. Now, the cool thing about Lustre is that it provides a massively scalable solution in terms of both performance and capacity. In order to do that, it would historically build Lustre file system on top of a large number of ext4, what are called backing file systems. The issue, or the issues with that, is that each individual ext4 would be limited in terms of its scalability and performance, and ext4 doesn't really have a lot in the way of features. It doesn't have anything at all in the way of integrity assurances. So ZFS, historically, has been a vertically scalable normal file system. In other words, the type of file system that Lustre could use as a backing file system. Unlike ext4, ZFS has a massive number of very powerful features. It has integrity assurances, which are very important for petascale deployments. For example, every ZFS block gets a checksum in addition to having RAID protections. Which brings me to ZFS is completely integrated as a quote-unquote normal file system and an advanced RAID stack. So ZFS merges the concept of RAID protection with the concept of a file system. So when you combine Lustre and ZFS, you essentially fill in the blanks of either of those two file system solutions. ZFS can't scale out horizontally. Lustre can. Lustre over ext4 scale vertically very well. You can't scale an individual OST very well with Lustre over ext4. Well, with Lustre over ZFS, you can. So essentially, Lustre plus ZFS is better together. Each piece fills in what the other was missing. Next slide. So, where were we at last year? Well, last year and the year before last, in fact, Lawrence Livermore National Lab was very actively trumpeting the horn of ZFS on Linux and has deployed it in their very large and very successful Sequoia system. Actually, they've now deployed it in a bunch of file systems at Livermore. And by all reports, the ZFS Lustre integrated systems at Livermore are the best performing and most reliable Lustre systems that Livermore has. Livermore being one of the largest HPC sites in the world, I think that's a reasonably good call to authority. So, a couple of years ago, I heard and I thought, well, Warp has a ZFS architecture, and we do parallel file systems, so maybe we should get in on this. And we've been working together with Livermore directly and on our own as well for that time to support ZFS Lustre integration commercially. Up till last year, we implemented that by using a separate ZFS RAID system connected via RDMA to a Lustre object storage server. So you would have a Solaris-based version of the ZFS volume management layer, and then you would have a Linux implementation of the ZFS file system layer merged with Lustre. So you did actually get all of the individual pieces of ZFS Linux, but it wasn't fully integrated. And from an HPC manageability standpoint, the fact that you had to manage Solaris was not really great. Even Open Solaris is not really what the HPC world generally likes to hear. So we continued the integration effort, and going on to the next slide, what has changed since last year? Livermore has continued to develop the code and refine it and scale out and debug things and get it working really well on all of the layers. So the volume management layer for ZFS on Linux got up to the point where we felt it was robust enough for production deployments. We therefore integrated the complete ZFS Lustre stack into our embedded controllers. So now you can get the file and block aspects of ZFS plus Lustre. That is the vertical file and the parallel file and the RAID style aspects of this, all running on a single fully integrated controller embedded inside our storage system. So there's no Solaris, there's no directly connected Infiniband RDMA cables, and you don't need external object storage servers anymore with our approach. And this allows us to deliver it as a much, much, much simpler turnkey appliance. Now, again, I don't suggest that all users need to buy this from us to get our hardware. They don't need to buy commercial support for us. A lot of HPC shops prefer to do it themselves. So another cool thing that has happened over the last year is it's become very easy to install this and get it working from a Red Hat-style Yum repository. I'll talk about that a little bit more later. You can get some commercial support if you want, but you can also get started on your own with it very, very simply for zero money and probably about 15 to 20 minutes of time. Now, why would you actually want to go to this style of HPC storage system? So there's quite a few file system level benefits, data integrity, advanced RAID features, and so forth. But some of the benefits are a little bit less intuitive. For example, if you have a complete ZFS Lustre integrated storage environment, you can pixie boot the entire thing and run it over, run the boot image over NFS such that all of your storage servers are diskless. In other words, you can manage all of your storage, that is the file system layer, the parallel file system, the vertical file system, and the block layer. You can manage every aspect of your storage in the exact same way that supercomputers manage the compute layer. You can orchestrate the storage layer. And if you've already got tools to orchestrate the server layer, you just use the exact same tools in the exact same way. Historically, you would have to run around doing complicated firmware updates and, worry about RAID. Is your RAID going to disappear once you've done this firmware update? You don't have to do any of that anymore. The storage layer just becomes a general purpose compute server from a manageability standpoint. Complete base OS control. The legacy OEM storage is all designed to lock you out of the operating system. They would like to pretend that they don't actually have Linux running on their controllers, for example. With a ZFS on Linux system combined with Lustre, you get complete control of the storage operating system in the same way that you have complete control over a server operating system. So, for example, with that control plus the fact that this is a completely open source stack, you can create your own tools. You can create your own features. You can do everything for the storage layer that you could do for the server layer today. Next slide. Now, continuing, more of the business value aspect is that this gets your storage moving in the same mainstream direction that HPC is moving in. That is, it gets your storage onto the open source track versus proprietary track. If you think about it, even 10 years ago, almost, I would say the majority of IT professionals, if you asked them about Linux versus Unix, well, Solaris is never going to go away. AIX is very, very important. It will always be important. IBM is backing AIX. IBM is IBM, so AIX is clearly the way to go. But proprietary Unix did not win out. There's considerably more development on the open source side, and it's hard to compete with free. You might want to pay a little bit of money for support. That's why people pay Red Hat when you could just do Linux for free. But it's vastly more cost effective to pay Red Hat for support than it is to, say, buy AIX from IBM. As a consequence, proprietary Unix became a declining market, and Linux became ascendant. The same thing is happening in the storage space. It's happening fairly rapidly. The legacy OEMs are scrambling to figure out how they will remain relevant in the years to come. And I think this is a good time for HPC to get on that train before it leaves the station, as it were. From a technical standpoint, you get really good compression ratios. Livermore has published metrics saying that their Sequoia system gets around 1.7 to 1 in real-world HPC workloads. Across the entire file system, that's their average compression ratio. So if you think about how much money you're spending per petabyte, getting 1.7x more petabytes of usable space out of that dollar helps a lot. And the fact that you're not paying a proprietary OEM the 500% markup on every disk gets you more leverage as well. Hybrid SSD pools, however, are potentially the biggest performance benefit for HPC shops. Lustre does not typically do well with reads compared to writes, and does not typically do well with small random reads in particular. ZFS allows you to bolt SSDs onto storage pools transparently, such that the ZFS RAID layer automatically caches frequently accessed data onto the read-optimized SSDs. In typical workloads, we've seen this increase small random read performance, or even small sequential read performance, or even large sequential read performance. We've seen this increase performance across the board dramatically. Now, something that a lot of people overlook is the integrity protection. In petascale systems, silent data corruption, bit rot, and similar RAID write holes become typical cases. So if all you're doing is using, say, MD RAID, Linux's built-in software RAID, it's not a question of whether or not you will get data corruption. It's a question of how many times it will happen in any given week. ZFS categorically fixes that. It uses a copy-on-write architecture, so you can't get RAID write holes. And it blocks at a block level. Every block is protected with a checksum. Bottom line is it has self-detection and correction for all known forms of data corruption. But it also allows you to run your own code directly inside the storage array. There are certain things that you don't, under any circumstance, want to run on a storage controller, like, in-user simulations and whatnot. But storage-related applications, like compression algorithms, CRAM, in this example, is a compression algorithm specific to genomics data. It can allow you to get, I kid you not, something on the range of 99% compression ratios. And that sounds like a ridiculous number, but it uses a deduplication style method of eliminating excess storage of data, which is incredibly efficient. So if you can run this directly on the storage controller, you can get leverages that are just almost unbelievable. And the flexibility that Warp gives you to run that on the storage controller is industry unique, frankly. So this isn't a sales pitch, but since I represent Warp, I'm going to use my own gear to illustrate how we do this. I should say right up front that groups within Livermore do use Warp systems to do this. Other groups don't. In fact, the largest file systems are not at the moment using Warp hardware. So you don't have to have our systems architecture that I'm going to describe in order to do this. So what we do is we implement the entire stack as an appliance. So if you see the picture at the bottom of this slide, that's a Warp Mechanics storage array. You can obviously see that it has disks. In the back of it, it's got two controllers, and the controllers are general purpose Sandy Bridge Intel servers. So one of the pictured boxes is actually a storage array and two object storage servers. So if you wanted to substitute commercial off-the-shelf hardware or COPS hardware, you would need a storage enclosure, JBOD, just a bunch of disks, hooked up to a couple of 1U white box servers would do the same general job. It's really just a question of, do you want it as a turnkey appliance with commercial support, or do you want to build it yourself out of commodity hardware? So the way to arrange this, as our basic building block, we take 3 of these 4U 60 drive slot chassis. We use 2 of them as JBODs to get more spindles, and one of them is a combination of a 60 slot JBOD and 2 Sandy Bridge object storage servers. So in total, that gets you a 180 bay object storage server, or HA pair of object storage server. We solve that as 100% hard drive, 100% SSD, or a hybrid of the two. Lustre Over ZFS supports all of those models. And depending on what kind of drives you pick and what kind of workload you're running, we get between 4 and 12 gigabytes per second per pod. So if you're doing like a pure SSD solution or a hybrid solution and get a lot of cache hits, you could pretty easily get 12 gigabytes per second. And, this scales linearly as you add more pods. It's, well, not quite linearly, but pretty close. And would yield a usable capacity of somewhere in the vicinity of a petabyte per pod, depending on what compression ratios you get, such that you could get multiple petabytes per rack, and potentially, 3 dozen or more gigabytes per second per rack. But this isn't the only arrangement we can support, and it's certainly not the only arrangement you could build on your own. If you want a higher ratio of performance, then you could put CPU-based controllers into every single shelf. You could get 3-4 times the performance that I just quoted with the same capacity if you just added more controllers and didn't use JBODs. In our system, the server is 0U. That is, it goes in the back of the storage controller just as a RAID controller would. So I'm not going to spend a lot of time on this slide, but the bottom line is it's an illustration of our Sandy Bridge controller. We have 10 gigabit Ethernet built onto the motherboard. It also supports PCIe 3 cards for Mellanox, Infiniband, or 40 gigabit Ethernet. So how you would arrange that into a Lustre ZFS production scale file system is illustrated here. This 4-rack system would, in a typical case, produce over 14 petabytes of usable space. That's using Livermore's compression ratios as an example. And in typical cases, it would be over 70 gigabytes per second. Now, that's the most aggressive scenario we can come up with. We can get 3 times or so the performance of that if we put in more controllers and more SSDs. We can also get higher density. For instance, if we use 6 terabyte drives, or we also have a higher density JBOD shelf we can hook up to this. So bottom line is, if you select whatever preferred high density hardware you want to use and select whatever server layer you want to use, you can get similar designs to this, wherein each subsection of a rack is an HAOSS pair with some amount of disk and some amount of SSD, and that'll yield a cost-to-performance ratio based on whatever your supercomputer needs you to achieve. Okay, next slide. So how would you actually build something like that? Well, we like the version wherein you hand us a PO and we roll it in and turn it on. Our appliance is really that simple. We even pre-build the RAID layer and the parallel file system at the factory before we deliver it. But, that said, do-it-yourself is an absolutely viable option. Everything about the ZFS Lustre integrated solution is open source. You do not require any proprietary software to make it work. So you can just hook up your own combination of, Supermicro servers or Quanta servers or whatever you want to use to commodity JBODs, download the code, and go. I will say that the Lustre documentation is a little bit incomplete in this area, and Livermore knows that, we know that, and we're trying to help with it. So there are differences in how you manage Lustre with ZFS. They're not huge differences. Controllers still have a management server. LNet works the same way it always did before. 99% of Lustre administration has not changed. But the way you create OSTs, the way you create, the MGS and NBS, this has changed. So you have to use the backfs type equals ZFS, and this syntax is different. And as you're creating OSTs, etc., you also specify things like the RAID mechanism used. Is it RAID Z? Is it RAID Z2? Is it a mirror? And you can specify whether you want to add SSDs to the RAID as cache. And I've got a couple examples below. Next slide. But more to the point, we've got a QuickStart guide. So you don't have to really get the entire process out of this very short presentation. We've been going back and forth with Livermore to complete reviewing a publishable QuickStart guide. 10 minutes or so would allow you to get a Lustre ZFS virtual machine running. It's not intended to be a comprehensive administration guide for Lustre or ZFS. As most of the people on this call probably know, a comprehensive guide for Lustre is a gigantic, gigantic thing. And since 99% of it doesn't change when you use ZFS, trying to reinvent the wheel on that would not be productive. So what we did is distilled down only the things you need to do to get a Lustre over ZFS proof of concept VM running and gave you cut and paste commands and explanations of what they do. So the little blurb down at the bottom has an example of what's in the QuickStart guide. It says things like, edit etsy.ldeb.conf and make sure it has the following lines in it, paste. If you want to get an advanced copy of this before Livermore gets it posted, just go ahead and send an email to lustre@workmech.com, and we'll reply back with the PDF. Otherwise, it'll get posted on ZFS on Linux.org and some other places once the review is complete. Next slide. That essentially is it.
Well, thanks for that, Josh. I wanted to go back to this the before and after piece, right? Because last we talked, you still needed that Solaris component. What has changed? Did the Linux implementation mature enough that you could move away from that, or what would you say?
Sure. So that's a big part of it. When we originally started going down this path, the Linux ZFS implementation had really just started, and there were a lot of missing features from the volume management layer. This was because Livermore had prioritized the file system aspects of ZFS and not the volume management aspects, because they had kind of missed the window to implement a completely converged solution when they built Sequoia. The ZFS stuff wasn't completely ready by then, so they had gone off and bought a big pile of RAID arrays, and that was going to provide the volume management layer. And then you ended up with a little circular logic. That is, they didn't have the volume management layer completed, therefore they had to use an external proprietary RAID, therefore prioritization was lower on the volume management layer, right? So it just took longer to get the volume management layer refined, but we're now at the point where Warp is comfortable supporting it commercially, whereas we weren't last year.
And as far as the value of this, Josh, I mean, it looks like you can deliver performance, but what am I giving up when I get the goodness of ZFS underneath this? Am I giving up, application performance? What? There must be a catch.
Well, of course. Sure. So there's always trade-offs. For example, the OEM storage systems have considerably more years and megabucks invested in management tools. So let's say that you really like a GUI mechanism of creating RAIDs. Well, we're not really about that. We do have a GUI, but it's kind of primitive and more of a checkbox feature than anything else. So I would say management tools and refinement of management tools is the main thing you're giving up.
Sure. And then I was intrigued also by this idea of doing the processing where the data is stored, right? Because these controllers happen to be pretty powerful Xeon devices, because that's what gets you the bandwidth, right? So is that something that takes another level of complexity to make happen, or how do you work that?
Sure. So it depends on what you're trying to accomplish, whether it's complicated or not, depends on what you're trying to accomplish. And also depends on whether you use Lustre over ZFS versus using something like de-dupe over ZFS or Ceph over ZFS or so forth, because we actually support integrating other parallel file system style gizmos besides Lustre. So if all you want to do is run an application on the OSS that, say, migrates data around. Let's say you wanted to build an HSM-style application, the hierarchical storage management, to move old files to a backup directory or something. Really, that's just the same level of effort that you would put into building that application on any other Red Hat-style Linux platform. You build a Perl script, you put it in a cron job. Call it a day. Because we do give you complete root level control over the operating system, and it is really just CentOS. It's CentOS with a bunch of HPC style tweaks and performance tunes and Lustre and this and that, but at the end of the day, it's CentOS 6.5.
Right, right. Well, kind of a wrap up here, Josh. I mean, there was always this question about, can you actually ship something with ZFS on it without worrying about, legal issues? And it sounds like you can deliver a box with all this implemented.
Yeah. So the question comes up because of a weird and unintended consequence of the GPL wording compared to the CDDL wording. So the open source licensing agreements are worded a little bit differently, and so people say, well, can you ship something that's CDDL on a GPL system? People have asked Linus about this, and he said, no, I don't care. I think that's kind of a strange position for lawyers today.
Mm-hmm.
Kind of his response to it.
Yeah.
Free is free, right?
Right.
On the other hand, if customers are worried about it, if somebody thinks they're incurring liability by doing this, I would encourage them to consider the following. First, who would actually file a lawsuit about this? Who would have standing and care to file a lawsuit?
Mm-hmm.
Second, who's doing the development on this? It's not the customer and it's not Warp. It's the United States federal government.
Yes.
So which corporation is going to have the, for want of a better word, balls, or stupidity, if you like, to sue Lawrence Livermore National Labs over this and alienate their, So I just don't think it's a real issue. But if you believe that it is, we can completely get around it by doing the code installation at the customer site. That absolutely solves the problem.
Yeah, yeah. Well, terrific. Well, Judd, this is really intriguing, and I'd love to hear more as you guys get traction out there, because it sounds like it solves a lot of things with Lustre that people might want there out in the enterprise.
Mm-hmm.
Well, great. Well, hey, Josh, I want to thank you once again for coming on the show today.
Great. Thanks for having me.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of high-performance computing.